All right, we are now going to start the second chapter of um, our curriculum, and it's going to start with inequalities, which will be the first couple sections, and then we'll talk about inequalities with two variables. Today we'll focus primarily on one variable, and then after that we'll deal with some absolute value functions. Okay, this particular section has two learning targets, and that's that you can find and solutions and graph simple and compound inequalities with one variable, and then use inequalities to represent some sort of real life situation. Okay, so this section will be primarily a review of things that you would have learned at some point in Algebra 1, and so we'll just get going through it. Okay, so we want to solve inequalities in one variable. Okay, so as I'm looking through this here, what we're going to do is we're going to figure out how to solve for x, represent our solution, and what that means. So the thing that's really nice about this is often solving these equations really can just be essentially the same as solving equations with some minor differences. So I have 2x minus 4 is less than negative 24. So as I look at this problem, I'm asking myself what values of x is going to make this entire side here less than the value of negative 24. So as I'm working through this, I am just going to try to solve for x the same way. So the properties of equality are the same, or mostly the same as the properties of inequalities. So if I, for example, if I want to add 4 to each side, I can do that, and the inequality will retain its inequality, I suppose. All right, so if I add 4 to each side to kind of undo that minus 4, you're going to get 2x is less than negative 10. Okay, so then 2x, hopefully we know at this point, means 2 times x. If I want to undo multiplication, I'm going to divide. Okay, so then I divide, and I am left with x is less than negative 10. Okay, so what does this mean? This means if I want x values that are going to keep this top inequality true, I need to pick x values that are less than negative 10. So we can represent this. So in general in my class, what I think is perfectly fine is you don't actually have to write the whole number line out. Just give me two numbers. The first one will always be 0, and then the next one is like your critical value here. So my critical value is negative 10. So I'm going to go ahead and put 0. It doesn't really matter where. I suppose 0 can be right here. And then negative 10, well, it doesn't look like I have 10 spaces off to the left, so I'm just going to go like negative 2, negative 4, negative 6, negative 8, negative 10. And I'm looking for x values that are less than that. So really, as I'm looking here, it's all these values kind of over here, right? Less than negative 10, okay, right? Because this would be negative 12, this would be negative 14, etc. All these values are less than it, as opposed to here, like negative 2, that's greater than negative 10. That's not a solution. Same here. This would be 4, not a solution. And so all these values off to the right of negative 10 are not solutions. They're not going to keep this top inequality true. Okay, those would make them greater than or potentially even equal to. So I know it's all of these values out here, but what about negative 10? Is negative 10 a solution to this? Well, we could go ahead and test that. Okay, so if I wanted to, I could say, hey, 2 times, well, I'm testing negative 10. Minus 4 is less than negative 24. This is negative 20. And negative 24 is less than negative 24. Well, this is actually not a true statement. So that means negative 24 is not, or negative 10 is not a solution. Okay, it's not a solution. But I know all the values to the left of it are, because those are the values less than that. So how do I represent that on my graph? Okay, well, this is pretty much standard way you're going to see it, but also this is how I want to see is open and close circle on your critical value. So my critical value is negative 10, okay? And so just go ahead and put an open circle on it, okay? If that critical value is not part of the solution, you're going to keep it open. You're not going to fill it in. But if it is part of the solution, it would be less than, or you would fill it in. So I'm just going to shade off to the left-hand side because that's where all my values are. So based on this graph, I can pick any number on this number line. Okay, that's in my shaded region, but not in that circle because that circle's open. It's telling me -10 is not part of my solution set at all. And so these are all my solutions here. Now, if this was less than or equal to, that would be the situation where I would want to shade -10 because then that would tell me it's inclusive. So, in general, open circle is going to be exclusive. That means it's not part of the solution set. Okay, it's exclusive, and you're going to see that with less than signs and greater than signs. Okay, a closed circle is going to be inclusive. Okay, it's inclusive. That means it is in the solution set. It's part of the solution set. That's going to come with less than or equal to and greater than or equal to, because it's or equal to. That or equal to part tells me that that's part of the solution. Okay, now it's important to note that, all this work here, kind of off to the left, and then this graph here, that's kind of my expectation of what I would like to see. This is not necessarily part of my required work here. This was me just kind of showing you that -10 is not really part of the solution set, more or less me trying to just make a point. So this is not required work. Okay, let's have you pause the video, move on to letter A, and try it on your own. Okay, so now we're going to try this one on our own, and so I'm assuming that you've already done that and you've already tried it and you're checking your work. Okay, now I'm going to start by subtracting -2. Get -5y is greater than or equal to -15. Okay, and then I have to divide by -5 here. Okay, and when I divide by -5, let's just read this statement. The opposite of y is greater than or equal to -15. So that means the opposite of 5 times y. Okay, or -5 times y. So this is something that hopefully you just remembered from like your Algebra 1 course. If you didn't, that's fine because you're about to be told now. When you multiply or divide by a negative number, you flip your sign. So really, when you're talking about inequalities, solving them, really the process is going to be basically the exact same thing, with one pretty major exception here that I've written in red, and I would suggest maybe you do the same if you didn't remember that, which would be when you multiply or divide by a negative number, you need to flip your sign. Okay, so as I'm doing this, this becomes a positive y, and now I just need to literally flip my sign. So greater than or equal to is going to turn into less than or equal to. Okay, and -5 or -15 divided by -5, well, that's just going to be a +3. Okay, so as I'm looking at, as you're checking your graph out, I want to see two numbers. The first would be 0, and the second is like your critical value, or like your boundary value. Okay, and so it's 3, so that's going to be to the right. 1, 2, 3. So this graph we can go by ones. Okay, so let's think about what I talked about in number 1. Like, is this going to be, like, this one was an open circle because -10 is not part of my solution set. Well, this one here, y is less than or equal to 3, it's or equal to. So that means if my value is 3, it's going to be part of my solutions. Okay, so this is going to indicate to me that I would like a closed circle. And this indicates to me that 3 is inclusive in my solution set. Okay, y values that are less than or equal to 3. Okay, less than or equal to 3. So like less than, right? So I'm looking for values with smaller values, such as 2, 1, 0. So really, I'm looking here. This is 2. 2 is less than 3, so I know I'm going to be shading off this direction. As opposed to this value is 4. 4 is not less than 3. It's actually greater than 3, so I wouldn't shade over here. I would be shading off to the left. Okay, and so then we're just going to shade off to the left. Alrighty. And again, as far as your graph goes, I don't care where 0 is at, or really even so much as where your critical number is at, as long as you're like kind of following a scale. Like for here, I want by values of 2. This one I'm going by values of 1. And as long as I just see where 0 and that number is, that's really all I need to see. I don't need to test pretty extensively on what a number line is going to look like. Okay, so now I'm going to move on to 2. And 2 really is just going to follow a lot of the exact same stuff that we just covered. It's just going to have a couple extra steps, right? So on 1 and A, our variables were already pushed to one side of the inequality, and then we had to solve. This one, we'll have some variables split up, and then we still need to solve. Okay, so I'm looking at this, and I have 12 minus 3t is less than or equal to the opposite of t plus 6. So for myself, I like to try to get all my variables on one side of the inequality or equation, doesn't matter, and I want to just get those on the same side, and then I can start manipulating the inequality or equation at that point to get all the constants values grouped together as well. So if I want to get my inequality, or if I want to group up my variables, I think it's going to be pretty easy. Like here, opposite of t or minus t, the best way to undo that is just add a t value to each side. Okay. One thing, especially if you end up taking higher level math courses, this is kind of off topic, but if you're using t as a variable, I would really suggest putting a little tail under it, like I did here, so that you can differentiate the difference between plus signs and t variables. Not a major thing, but it is quite helpful when I'm looking at your work, and really for yourself, as a matter of fact, too. Okay, so then next, now that I've gotten all my variables grouped together on one side of the inequality, I want to try to get rid of the constants, okay? So I have constants of 12 here and 6 here, but I don't want my constants moved from this side to this side because I already have my variables condensed on the left. I want to move my constants from the left to the right side. So that means this 12 has to be dealt with, okay? So this is a positive 12, so if I want to get rid of this, I'm going to have to subtract 12 from each side. Okay, and so then I have negative 2t is less than or equal to negative 6. Okay, and so then I'm just going to write the rest of my work up here. So I have negative 2t is less than or equal to negative 6. So if I want to get that t isolated, now I can get rid of my coefficients, and I can get rid of my coefficients by dividing or multiplying. So here I have negative 2t. I want to undo this by dividing by negative 2. Okay, and then from this point, I'm going to get t is greater than or equal to positive 3. Okay, so again, here I had to flip my sign because I'm dividing by a negative here. Okay, because it kind of has just this opposite nature, so it just requires you to flip your sign. Okay, so the two numbers I need to see are 0 and 3. So I'm actually going to put 3 here, I guess. 2, 1, 0, and 0 here. And I'm just really putting it off to the right side because I'm kind of as lazy as possible. I want to have to shade the least amount of work, but it doesn't matter. You can put it basically wherever you want. Okay, so then I have to ask myself whether 3 is part of the solution or not. You know, if I were to plug 3 in here, 3 is greater than or equal to 3. Well, 3 is equal to 3. Okay, so this is going to be an inclusive critical value or boundary number. Okay, so that is inclusive, so 3 is part of the solution. And I'm looking for t values that are greater than 3. So as I look here, this is 1 and 2. Those values are less than 3. So I know that these aren't part of the solution. But here is 4. 4 I know is greater than 3. Therefore, I know it's part of the solution. So I want to shade on that side. Okay. So one thing that, you know, may need to be brought up is that solutions either lie on one side of that critical value or the other. You can't have solutions here and here simultaneously at the same time. Okay. Also, pretty important to know that, you know, I could have started by adding 3t to each side. Okay. In general, I find it easier to find where my solutions are if your variable's on the left. but that's definitely not required. Okay, all these problems can be done either way. So what is a good idea for you is to pause the video, try letter B on your own, and then check it with my work right now. So I'm assuming you've already tried this and you're just here to see how you did. Okay, so I have 1 minus 4x is greater than 1 minus 2x. So I'm just going to add 2x because I want to get all of my variables condensed into one side. And so now I have 1 minus 2x is greater than 1. Okay, and so then at this point here, I'm just going to subtract 1 to get the opposite of 2x, or negative 2x is greater than 1 minus 1 is 0. Okay, and then I need to divide by negative 2 to get x is less than 0. Okay, I still need to flip that sign because I divided by a negative. Okay, so in this situation, I just need to see 0. That's the only number I'm going to need to see. So I'm going to put 0, let's say right here. Okay, and then I need to figure out whether 0 is part of my solution set or not part of my solution set. So I'm looking at here, 0 is less than 0. Well, that's not true. 0 is equal to 0. So that means it's not part of the solution. So I need to put an open circle here, indicating to me that 0 is not part of the solution set. And I'm looking for values that are less than 0. Well, here's 1 and 2. Well, 1 and 2 are greater than 0. Here's negative 1 and negative 2. Those values are less than 0. So I want to shade off to the left. Those are where my solution lies. And any x value in our shaded region is considered a solution. Okay, so one thing I want to point out is that based on the problems that we did, the inequality always pointed the direction you shaded. And this isn't always true, but I'll set you up in a way so that it will always be true for you. So if your variable is to the left of the inequality, then it will point the direction you shade. Okay, now I could have given you this rule right off the bat, but I want you to understand what a solution is. A solution is one that is an x value or t value, whatever variable value that makes this first inequality true. So will this be a good, helpful hint for some of you? Absolutely. But for the most part, I would really prefer you just to kind of think about, well, is this part of the solution or is it not? And then where do I have to shade based on this? Although if your variable is set up to the left, it will point the direction you shade. So x is less than 0, it's pointing to the left. X is greater than 3, variable's to the left, so then it's pointing to the right. Okay, so again, that's only true if the variable's on the left-hand side. Okay, so what I want you to do is just pause the video and actually just write yourself down some things that you believe are the same as solving equations in comparison to solving inequalities, and then maybe some things that are different. Okay, so what's the same? So hopefully after you did some work, you figured out that, like, multiplying and dividing here, like if you do it to one side of the equation, you have to do it to the other. Right? If I divide by negative 2 here, I have to divide by negative 2 there. The same is true with adding and subtracting. Okay? As I do that, those methods are really the same. Okay? So different. What's different? Well, the biggest difference, I think, which may jump out to you right off the bat, is flipping your sign. When you're solving an equation, you really never have to flip any sign whatsoever. It's never even really anything that even really has to cross your mind. Okay, what else is different? Okay, this one, hopefully some of you thought about, but when you solve an equation, at least a linear equation, you tend to just get one number. right? You just get a number. This is what it should be equal to. Well, in this one, are you just getting one number? Let's think about it. Let's just look at number 2, for example. I get t is greater than 3, so I know I only have like one number here, but t can be 3, it can be 4, it can be 3.5, it can be 4.1, it can be 87. Okay, so really how many solutions am I getting? I'm getting infinitely many. I'm getting infinitely many solutions. Okay, it's just that in that set of infinitely many solutions, I can define specifically what numbers those are. Okay, so that's one thing to think about. Okay, so what we just did were called simple inequalities, okay? And so let's actually go ahead and just use a simple inequality to maybe solve something that's a little bit more of a word problem, set us up to help us understand how they may work. So admission to an amusement park costs $9, and each ride ticket costs $1.50. So as I'm thinking about this, it's going to cost me $9 just to get through the door, and then every ride I want to ride is going to cost me an additional $1.50. Okay, you only have $45 on a particular day. Define variables and write an inequality to describe the number of rides that you can, or ride tickets that you can buy. Then solve and go ahead and give a solution. Okay, so as I'm looking at this, let's go ahead and define our variable. Okay, often defining variables will help us determine, well, what is, how are we going to answer a question? It's also the moving part, the part that is constantly changing. Well, what's not changing is the amount of money that I have to enter the amusement park. It's just $9. It's not going to change. But the amount of money I pay to ride rides is going to change. That's going to fluctuate depending on the number of rides I take. Because if I ride one ride, it's only another $1.50. If I ride two rides, it's going to be $3. Okay, so this is going to be the number of ride tickets purchased. Okay, and so let's write our inequality. So I know that if I want to figure out how much money I'm going to spend, I'm going to take the money spent to get in the door. I'm going to take that, and then I'm going to take the money I spent on rides, and I'm going to combine it together. That's going to tell me how much money I spent. Assuming that there's no other variables such as food or anything like that. So as I'm taking that, well, how much money did I spend just to get in the door? Well, it's $9. So I'm going to take my $9, and I'm going to add to it the money spent on rides. So the money spent on rides is going to take $1.50, and I'm going to multiply it by the number of tickets I bought. For the same reason I talked about a moment ago. One ride is $1.50. Two rides is $3. Three rides is $4.50. All I'm doing is taking $1.50 and I'm multiplying by the number of rides. So I'm going to take $1.50 and I'm going to multiply it by the number of rides or ride tickets I bought. But I don't know how many ride tickets I bought or don't know how many ride tickets I can buy. So what is that part? Well, that's exactly where the variable is going to come into play. This is the unknown part. This is the part that's fluctuating. That's our variable. So if this is going to represent the money I spent on any particular day. And what do we know about this money? We know I can only spend $45. So I know I have $45 to spend. So what does that amount that I have on the left, the money that I'm figuring out how many rides I can, what does it have to be in relation to 45? Could it be greater than? Can it be less than? So as you think about that, think about if you only have $45, the amount of money you spend has to be less than. So hopefully you started out with at least something like this, less than. It has to be just less than. Now the other part is, well, there's two parts to less than, just like there's two parts to greater than. There's less than or equal to. There's also greater than or equal to. So you need to ask yourself, we know it's less than, because I can't spend more than $45. But can it be equal to $45? If you have $45 in cash, can you spend exactly $45? And the answer to that is yes. So this would be a situation where, yes, you can spend $45. So this is going to be an example of less than or equal to. So this represents our situation. And now we just have to solve it to figure out how many rides I can have. Okay, so I'm going to subtract $9. Then I'm going to get $1.50 times the number of ride tickets purchased is going to be less than, and that is 36. And then I'm going to divide by $1.50. So I know that x has to be less than or equal to, well, I don't really know what 36 divided by 150 is, so let's go ahead and just check that out. Okay, and that's 24. So x has to be less than 24. Okay, so the number of tickets purchased has to be less than 24. Okay, so, what does that mean? If I have 0 here and 24 here, I can buy 24 tickets, but I have to spend less than that. Okay, now, one thing to think about, even though that this is just a very basic example of an inequality, can I buy negative tickets? Not really. So, what does this mean? I know that I really can spend between 24 and 0 tickets. Can I buy 0 tickets? Yes, I can. Okay, so even though the setup for this one ended up being a simple inequality, what this is here is a great bridge into compound inequalities, because I can buy less than 24 tickets, but I can't buy negative tickets. It doesn't make sense. Okay, so we can spend between 0 and 24 tickets, and anything in between, including 0 and including 24, and that is what we're going to work on right now. Okay, so when you have a compound inequality, which is exactly what I just talked about, is where I have two boundaries. I have like, hey, it has to be less than this amount and greater than this amount. There's two types of compound inequalities. There's and inequalities and there's or inequalities. So let's talk about the difference between the words and the words or. And we're not even going to talk about math. We're just going to talk about like the literal difference between those words. So for example, if you go home and whoever you're living with says to you, you cannot hang out with your friends this evening unless you do the dishes and take out the garbage. So what does that mean? That means that I have to do both of those. I have to take out the garbage as well as do the dishes. Once both of those tasks are completed, once I check both of those boxes off, I can go hang out with my friends. As opposed to, and if they stated it like this, you cannot go out with your friends until you until you take out the garbage or wash the dishes. Now that statement's completely different from the first one. They sound very much the same, but they are different. Because this one says you just have to do one or the other. Once you've checked one of those boxes off, it doesn't matter. It's done. You've completed your requirements. So that concept has a big impact on what we're about to do with and inequalities and or inequalities. And what it will do is we'll talk about solutions. So I'll try to relate back to this here in a moment. So one thing mathematically speaking now is that and inequalities will either be written with the word and, or it will be bridged together like this. Any inequality that has like a number or an expression, inequality sign, another expression, it's written like this. This is automatically an and inequality. Okay? Or inequalities will always have the word or. They'll never push them together. So you really don't ever have to concern yourself about or inequalities. It's always an or inequality if it has this little word or. And inequalities can be written as two separate ones with the word and, or if it's written condensedly like this, it is an and inequality. Okay, so I'm going to show you how we can solve these problems a little bit longer than maybe what you've seen before in the past, but hopefully it will help you understand more about and inequalities as well as or inequalities. So really an and inequality is just two inequalities like pressed together. And the first inequality is like the first two parts. 4 is less than x plus 5. Okay, and the other one is x plus 5 is less than 4. So really I kind of just split it with that middle part, kind of is going to be part of the left one and the right one. Okay, so let's go ahead and solve this, because we can solve each of these. So a compound inequality is quite literally two simple inequalities pushed together in one method or another. This is a simple inequality, this is a simple inequality. Then pushed together into 4 is less than x plus 5, which is less than 7. That is a compound inequality. So I'm going to go ahead and subtract 5. And then I get negative 1 is less than x. Okay, but to me, if I were to try and graph that, I would have to think about how, well, I know where my critical value is, but I wouldn't really know where I would shade. So you can go ahead and put that variable on the left-hand side, which to me is easier to comprehend just by thinking about it, as well as it has that trick of it tells you where to shade. But if you want to move things around an inequality sign, that inequality sign has to flip with it. So here, negative 1 is less than x is the same statement as x is greater than negative 1. Let's go ahead and solve the right-hand one. Okay, so this is x is less than 2. Okay, so what I'm going to do is I'm going to graph this first one on this top one. Okay, so let's say x is less than 1. So let's go ahead and put 0 here. And what I want to do here is I'm going to put 0 in the same spot on all of them. Okay, and I'm going to put negative 1 right here. And I know that x needs to be greater than negative 1. So is it an open or closed circle on negative 1? Well, is negative 1 part of the solution? No, because negative 1 is equal to negative 1. It's not greater than, so it's an open circle. And I'm going to shade off to the right. So this top graph represents all of the solutions to that first simple inequality. That first simple inequality is the solution set to this, just this part. So if I were to cover up this right-hand side, what I just graphed, those are the solutions to that. Okay, so I'm just going to put negative 1 here because I will use that. And then here we're going to put 2 because that's my other boundary value. Okay, so then the other one, this inequality here, I'm going to graph right here. And open or closed circle, well, it's an open because 2 is not less than 2. It's actually less than or equal to. So I'm going to put an open circle here, and I'm going to shade off to the left. Okay, so then the compound inequality is me pushing together those two solution sets. But we got to think about what are my solutions, because it's an and inequality. So this is where that analogy comes together. If I want to go out with my friends, I have to wash the dishes and also take the garbage out. So a solution for an and inequality has to be true for this inequality and also true for this inequality. If it's true for this one, but not for this one, it's not a solution. You have to have a solution that's true for each. So where is that going to be at? So let's think of this number, for example. This is 2, 3, 4, 5. This is the number 5. This is a solution to this first inequality, but it's not a solution to the other one. It's outside of my solution range. Okay, so where am I going to do? So I'm basically, if you think about pushing these together and taking the overlap, imagine me squeezing these together, and the overlap is what I'm going to take. Where is that overlap going to be? It's going to be in between negative 1 and 2. Okay, so what does this mean? Well, I know my numbers are between 1 and 2, but what about negative 1 and what about 2? Well, easy question. We know that solutions have to be true for, we know solutions have to be true for this one and for this one. Well, is negative 1 a solution for this one? No, it's not. So does that mean negative 1 is going to be a solution to the entire compound? No, it will not be one because it has to be a solution to both, so it's going to be an open circle. What about this one? Is this a solution? No, it's not a solution to this one. Even though it's a solution here, this means it's going to be an open circle because it has to be a solution to each. and then everything in between. It's important to note that if you kind of got where I was going with this, this was strictly to demonstrate where I'm getting solutions from. I only need to see this bottom line. And as a matter of fact, in your homework, test quizzes, all that other stuff, you're only going to be given one line. Okay, but this was just to try help and demonstrate where my solution sets are coming from. Okay, so algebraically, my inequality is x is greater than -1 and x is less than 2. Okay, or inequalities are probably a little bit easier. So, because one, they're already split up. So let's go ahead and do this first one. So here I can just subtract 3 to get x is less than or equal to 1, or x minus 6 is greater than or equal to -1. I'm going to add 6 to each side. That's 5. Okay. So let's go ahead. Let's mark 0. Make sure we're marking it in the same spot. So, and that means 1 will be here. 2, 3, 4, 5. 5 will be here. Okay. And let's graph. So the first one I'll do up on the top, so that's right here. That's a closed circle on 1, because 1 is a solution. And then here is an x is greater than 5. That's this one here. So hopefully some of you are, really paying attention to what I previously said, and I'm thinking, well, there's not going to be any overlap here, so it must be no solutions. Well, this one is a little bit different because of that word or. Or, just like this statement, you can't go see your friends unless you wash the dishes or take out the garbage. For an or inequality or for something to be a solution to an or inequality, it has to be a solution to this one or this one. It doesn't matter which one, but if it's a solution to one or the other, it's a solution. So that means I can take all the solutions to the first one and just mix it with all the solutions to the other one, because it doesn't matter where it's at. As long as it's a solution to one, it's going to be a solution to the compound altogether. So this one, you're just going to kind of drop everything down and take everything they have to give you. So I'm going to go at -1 here, and it's going to be like that, and then here at 5, and it's like that. Okay, so this here's my algebraic representation of my solutions, and here's my graphical what I'm looking at. Again, I'm not going to need to see these first 2 lines. They're just here to help you demonstrate how you can get your solution set on your graph. Okay, anything in the shaded region is a solution. Here, anything in this shaded region is a solution. Okay, one thing that may help you is and inequalities and or inequalities. Okay, and inequalities will look like this in general. Okay, this may be open, it may be closed, but it's going to be in the middle. Okay, and what is it going to create? It's going to create a little I land. Okay. Okay, and inequalities are going to create little islands. Okay, they're going to create little islands kind of pushed together. Okay, where or inequalities, okay, these ones are going to kind of shoot outwards. Okay, and what are those going to create? Those are going to create the or, going to create the oars on a boat. So if you can imagine this being kind of a pretty terrible boat, maybe with a little sail in it. I don't know if a boat that has a sail needs oars, but this one does. Okay, so what is it going to do? My solution set is going to be outward like the oars on a boat, where and inequalities are going to come together to create like an island. Okay, so just some little tricks that maybe help you remember these. But if you kind of know your principles about and inequalities and or inequalities in general, they will work out. Okay, so what I want you to do is pause the video, try C and D on your own, check it here in a moment. All right, I'm assuming that we've already tried these and you're here just to see how you did. Okay, again, I am probably going to show you that I only need one graph here and that I'm not going to make these other ones. Again, these other two were here to demonstrate how the final solution set's made. You do not need those, but if it helps you, by all means. Okay, so the first one is an OR inequality. So I'm kind of expecting just preempting, I'm expecting my graph to shoot out like the oars on a boat. Okay, so here I need to divide by -1 to get the x variable by itself, and then I'm going to have x is less than -4. Or this one I'm going to add 6 to get -2x is less than 6. And then I'm going to divide by -2. And then I have to flip my sign to get -3. So I'm looking for x to be less than -4 or greater than -3. So let's put 0 here. -1, -2, -3. Well, actually, I'm only doing the bottom one. 1, 2, 3. So that's -3, and this is -4. Okay, let's just kind of graph this first one. X is less than -4. That's an open circle at 4, and I'm looking for values less than it. Well, -3 is greater than -4, so I'm kind of looking for the other side, -5, -6. All those values are less than -4, so that's going to kind of shoot out this direction. Okay, -3, so x is greater than -3. Again, that's an open circle, and it's going to shoot out off to the right. Okay, and then there is my oars on a boat kind of shooting outward. Okay, this one is an and inequality. Okay, so I am going to, I still prefer to split these up when I do these. So I'm going to split these up, but I'll show you a way where you don't have to split them up. Okay, so the first one is, I'm going to write the first inequality. It's like this. And then I'm going to subtract 8 to get -9 is less than or equal to 3x. And then divide by 3 to get -3 is less than or equal to x, which is the same statement as x is greater than or equal to -3, right? I can flip my inequality around as long as I flip the sign with it. Okay, the other one would be and 3x plus 8 is less than or equal to 8. So this -8. So 3x is less than or equal to 0. Divide by 3. X is less than or equal to 0. Okay, so here the only values I need to see are the boundary of 0 and -3. Okay, and the other ones where I want to see 0, and then I want to see your two other boundary numbers, like the edge of the inequality. Okay, so let's go ahead. Let's find 0, because that is a boundary value. So let's go ahead and put 0 just dead center. And then we're going to have -3 as well. 1, 2, 3. So there's -3. Looks like it's both closed circle because they're both or equal to. So I can kind of fill in the dot here, fill in the dot here. And I'm expecting it to be in between, but let's just check the inequalities to really make sure. X is greater than -3. So what values are that? Those are values off to the right. So I'm going to start shading off to the right. X is less than 0. Those are the values to the left of 0. So that is how we can do it. Okay, so that's how you would do it when you're splitting it up. Okay, which is fine if that's your preferred method. I am going to show you a little bit of a shortcut. But if you feel like you don't need that shortcut, this is good enough for you, skip on past this to the last example. But if you want a little bit of a shortcut, I know some students really like this, just make sure you know that it's an and inequality. But what you can do is you can kind of just solve it, but whatever you do to one part, you have to do to all three parts, right? There's a left part, a middle part, and a right part. So if I -8, I have to -8 over here. Okay, and so then that's -9 is less than or equal to 3x, which is less than or equal to 0. Then again, I'm going to divide by 3, but I have to divide all parts by 3. So this would be negative 3 is less than or equal to x, which is less than or equal to 0. Okay, so this statement, x is greater than or equal to 3, or greater than or equal to negative 3, and x is less than or equal to 0. This is the same statement. Negative 3 is less than or equal to x, which is less than or equal to 0. And one thing I will give this as quite a big advantage is that this represents on the graph pretty well, right? I would just graph negative 3, I would just graph 0, and then I would shade in between, which is kind of what this is demonstrating. Okay, I think this might help demonstrate what an AND inequality is, but if you already know what an AND inequality is, you watch these examples, you feel very confident about it, and this is less work for you, do this. I have no issues what method of choice you do. Okay, so let's go ahead and use compound inequalities to solve a word problem. We'll have a little discussion about it at the end, and then we will get going. Okay, so during a summer celebration, the basketball team is grilling hot dogs and selling them as a fundraiser. Each package of 24 hot dog costs $4, and the team can only spend at most $88 on them. Last summer, they went through 312 hot dogs, and they want to make sure they have more than the 312 hot dogs available to be made. Okay, define your variables and write and solve an inequality that represents the number of packages of hot dogs to be purchased. Then graph our solution. So obviously, we want to start defining our inequality, or defining our variable, which really, honestly, anytime you have a word problem, this should be your first step every single time. So what is our variable? What's the part that's changing? We know how much money we're spending off of hot dogs, packages of hot dogs, and we know how many hot dogs are in a package. And furthermore, it asks for us to define a variable and give an inequality that represents the number of packages of hot dogs sold or purchased. So that's going to be our variable. We know x is going to represent the packages of hot dogs. Okay, so there's two things going on here. There's like number of hot dogs altogether, right? Because I want to have 312 or more, I believe it says. Yeah, they want to have more than 312. And there's also money at 88, and they can really only spend so much money. So let's do the money one first. I kind of like the money one. So I know if I buy one package of hot dogs, that's $4. Because each package is $4. And so then if I buy two packages, how much money would I spend? I would spend $4 and $4. Well, what if I bought three? It'd be 12, 4, 4, and 4. Well, that's just 4 times the number of packages. So really, if I want to represent the money spent on hot dogs, that's going to be the price they are, $4, times the packages. Okay, so this is the money I'm spending on hot dogs. And it says at most I have $88. So I'm going to put that 88 here. We have to figure out what inequality sign I need. So 4x, what does it have to be in relation to that 88? So if I have $88 to spend on hot dogs, can I spend $89? I cannot. I don't have that much money. I can spend less than it, right? So we know that this is less than. And then the question is whether or not I can spend $88 on the dot, right? So I know I have to spend less than that because I only have so much money to spend. But can I spend exactly that $88? Well, it says I only have at most $88. So the most amount of money I can spend is $88. But that does mean I can spend $88. So this is less than or equal to. Okay, the other is dealing with number of hot dogs altogether. Well, I know there are 24 hot dogs in each package. So if I have one package, it's 24. If I have two, it's 48. If I have three, it's 72, I believe. Don't check me on that. Anyway, the important point that I'm trying to get across to you is that if I have the number of hot dogs in a package, I'm going to take the number of hot dogs in a package and multiply it by the number of packages I have. And so then we know that we're looking to kind of have a boundary of like 312. We want to have more than 312. So this is pretty important. So if I want to have more than 312, that means that, can I have 312? Is having 312 hot dogs the same as having more than 312 hot dogs? No, more than indicates that it's just greater than. It's not equal to. So in this situation, it's just greater than. Okay, so lastly, well, we kind of have two different inequalities here, which makes sense. We know that this is going to be a compound inequality. Is we need to figure out, is this an or inequality or an and inequality? Which is pretty important. Okay, because if it's an or inequality, I just have to make sure this is true, or I have to make sure this is true. One or the other is good enough. As opposed to an and inequality, that means this has to be true as well as this at the exact same time. They both simultaneously have to be true. So as I'm looking through this problem, you know, each package is $24 and they cost $4. The team can spend at most $88 on them. It doesn't really say anything about only one of those being good enough. So to me, in my mind, that means I really need to make sure both of these are true. And that's going to be an and inequality. Okay, they have these requirements and they have to meet both of them. They need to have more than 312 hot dogs and they have to spend less than $88. So let's figure out how many packages that means they can buy from the store. Okay, this one I'm just going to divide by 4. And that means x is going to be less than or equal to 88 divided by 4 is 22. I actually knew that. I don't know why I did it in the calculator. Accuracy never hurts. Okay, and so then 312, I'm going to divide that by 24, which is 13. So this is x is 15. X needs to be greater than 13, and this is an and inequality. The equivalent statement to that would be that 13 is less than my number of packages of hot dogs, which is less than or equal to 22. This statement and this statement are the exact same thing. Okay, so in these word problems where the numbers are a little bit bigger, if it's asking you to graph that, don't feel obligated to include 0. It's not the end of the world. Okay, so let's go ahead and say that like maybe right here is 13. And then this is 14, 15, 16, 17, 18, 19, 20, 21, 22. This will be 22 then. Okay, so open or close circle on 13. That's an open circle. And then 22 is a closed circle. And inequality kind of indicates that my shaded region should be in between here. But we should just double check. Less than 22, that would be to the left. Greater than 13, that would be to the right. So that makes sense to shade in between there. Okay. All right, so we just graphed our solution. Let's just answer some questions about this. Using the inequality above gives solutions to the inequality. So like anything in here. Can the team buy 13 packages? Well, the answer to that is no. How come? Well, I cannot buy 13 packages because although it would satisfy costing less than $88, even though it would satisfy costing less than $88, it would not satisfy having more than 312 hot dogs. In fact, it would give us 312 hot dogs on the dot. And whoever's in charge of this does not want 312. They want more than 312. So the answer to that is no. Essentially, it's not part of the solution set, right? It's on the open circle, which is exclusive, and this boundary is telling me that 13 is not part of the solution set. What about 22? The answer to that is yes. Why? Well, because 22 is going to satisfy spending $88 or less. Okay? In fact, I'm spending exactly $88 here. Okay? But what is it also? It's also satisfying having more than 312 hot dogs. Okay? Because this is kind of my lower limit for that. Having 22 packages would allow me to do that. So anything in between. Okay, one last thing. It is important to note that this is a little bit weird because this would include numbers like 13 and a half or 12 or 14.8. And that doesn't really make sense to have like 0.8 of a package, so you really would want the numbers in here to be the integers, which are just like whole counting numbers. Okay. Otherwise, that is the end of this lesson. I would ask that you go ahead and move on to the homework of this section. Otherwise, I will see you at the beginning of 2.2.